All right, so we learned how to obtain a distinguisher as a differential distinguisher. So next question is, so that distinguisher only helps you to distinguish reduced round of a cipher from a random permutation, right? Now the question is, how can I turn it into a key recovery attack? Okay, so I'm going to focus on Wang's differential attack on 16 round present and show what works in practice and what doesn't work in practice, okay? Because theory doesn't match practice most of the time. So in that paper, Wang obtains a 4-round characteristic, saying that, so this is hexadecimal notation, the 16-bit input. He says that if you have only differences for these two S boxes, as the input difference 7, after 14 rounds, the output difference will be like this, with probability 2 to the minus 62. So as you can see, this is larger than 2 to the minus 64. This is why he stops at 14 rounds. Otherwise, continue to have 15 or 16 rounds. So with a 14 round distinguisher, which is theoretically obtained right like this, he adds 2 more rounds to the bottom and try to recover the round keys from there. So assume that after 14 rounds, these are the outputs, okay? Then if you add 2 rounds, these bit differences affects these S boxes, okay? This is why we represent them as question marks by saying that that can be anything, okay? So if we add 2 rounds to the bottom of this characteristic, the output difference should be in the form 0 question mark, 0 question mark, and so on. So you can look at this like this. So at the end, after 14 rounds, we say that the output difference are on these S boxes as 9. Recall that these are not inputs, they are differences. So by looking at the DDT table, we observe that if the input difference is 9, the output difference can be anything, but they don't have a difference at the least significant bit. So let's go back and see why this is the case from the DDT table. Let's look at 9. As you can see, you observe some output differences with some probabilities. But here, the thing you need to realize that all of these output differences are even. As you can see, 2, 4, 6, 8, and so on. This is why you don't have any output difference here. But still, for instance, this 0 goes to here. Okay, so you should know the round keys that is affecting these two parts to, try to capture. But long story short, we realize that after 2 rounds, if you add 2 rounds with probability 1, these differences can affect these parts. So these other parts will have 0 differences. This is important because I have control in the input, right? Because I will, as an attacker, say that, okay, give me M plain text where the pairs have differences like this. Now, I cannot ask them what happens after 4 rounds because I'm going to attack 16 rounds. I have no control in the intermediate bits. So I say that after 14 rounds of encryption, give me ciphertext pairs whose XOR are in this form, where there are no differences here and there may be differences in the question mark places, okay? Once we have those pairs, what you are going to do is the following. I removed, of course, the permutation layer here, so these question marks are mapped there. So there are round key XORs, right? So you need to guess those round key XORs so that you can go back from here. Again, perform round key XORs and go back here. Then go back here and check if these differences are 9. Okay, so you are going backwards now. So this way, the round key that gives you these differences the more will be your secret key. So let me explain all of this in these slides. Attack procedure is follows. First, we start with data collection. So you gather M plain text ciphertext pairs with input difference, as in the case of Wang's differential, and output difference in this form again in the hexadecimal. But again, this is what happens after 16 rounds. Now we are going to partially decrypt the 2 rounds by trying every possible affected round key bits to see if it gives you expected difference. So key guess. Partially decrypt these pairs. By these pairs, we're talking this ciphertext with every possible key bits of rounds 16 and 15. That corresponds to S boxes with non-zero differences. Correct key should have the highest counter. By counter, we mean you increase the counter of that key if you observe this difference, okay? So this way you can maybe capture 40 bits or 80 bits, whatever, but remaining bits now easy to be obtained because you will be performing exhaustive search on a small amount of bits, okay? So for instance, with this attack, if you capture 40 bits of the master key, for present 80, you now 40 bits remain, but your exhaustive search is now 2 to the 40, which is very easy to do, okay? So here's an example. This is a very nice exercise or a homework, let's say. So we first take a 5-round characteristic because we cannot verify if this attack correct or not, right? Because I need to gather n plaintext, which is maybe the whole code book, and perform this many operations. So our laptops are not capable of performing that many operations. But if you shorten the distinguisher, so from 14 rounds, I reduce it to 5 rounds, like this. Now the total probability is 2 to the minus 22. Now I add 2 more rounds to the bottom, as in the case of Wang's attack. So instead of 16 rounds, we are going to attack 7 rounds, but the attack procedure will be the same. So what I'm going to do is to, choose a secret key, gather n plaintext pairs, encrypt them with that secret key, and obtain ciphertext pairs in this form, and I will only give you the plaintext pairs and the ciphertext pairs. Actually, you don't even need the plaintext pairs. You can only look at the ciphertext pairs, then partially decrypt them 2 rounds back, and increase the counter of those candidate keys when you observe this difference, okay? This way, you can capture the sum of the round key bits, okay? So, let alpha denote the input difference, x0 equals to 4 and x3 equals to 4. So I'm giving differences to these S boxes. And beta denote the output difference in the S boxes 4, 6, 8, 10, 12, and 14. By question mark, this is a common notation we use. This means that the difference can be anything. It can even be 0 or anything, right? For the sake of simplicity, we omitted the last round's permutation because it doesn't affect the security. You simply will modify the places. 2 S boxes in the 6th round and the 8th round, 8 S boxes in the 7th round are activated. So let's go back. So here, okay, the sentence says 8 S boxes in the 7th round, right? By this, it actually means this 1, 2, 3, 4, 5, 6. But actually, in order to know this 0 difference here, it will have 0 difference, but in order to know the real values, we have to know this bit. So in order to know it, you also need to know this bit, this S box and this S box. So this is why we say that these 8 S boxes are somehow activated. So in order to perform the attack, you have to guess, there is a round key XOR at the end. So you have to guess 4 bits here, 4 bits here, and so on. So 8 times 4, 32 bits has to be captured by you or guessed or tried by you so that you can go 1 round upwards. Then, after the permutation, you need to know only places of these bits. So here it says that you only need to know 2 S boxes in the 6th round, right? Because you only need to know key bits that's XOR to these parts. So, this one, this, and so on. So in total, this means 40 bits of round keys. So there are candidates of 2 to the 40 keys, and one of them is correct, right? So your attack would be to capture the correct one out of 2 to the 40 round keys. So for every candidate 40-bit round key, you can initialize 2 to the 40 counters TI to 0. Of course, in theory, you can do it, but most probably it will exceed your memory. You wouldn't have that much of memory or RAM. I mean, you can, of course, use a hard drive. So you can come up with clever ideas to not keep a counter for every candidate key. But the idea is as follows. Perform 2-round decryptions on ciphertext CI and CI XOR beta. Increase the counter TI if after 2 rounds of decryption, the difference is in this form. Sort the counters TIs to find the correct key. Okay, so in theory, this is how a differential attack works. But here's the remark. We expect the correct 40-bit round key to get the highest counter. But in practice, some round keys might not be independent from others, and they might get the same counter as the correct key. So when you perform this experiment, check if this is the case. But since I'm saying this, you can get the idea that this will be the case, okay? This is also important to show why experiments are really important for cryptanalysis. Because in Wang's paper, they say that, of course, we reduce it into 7 rounds, but in Wang's scenario, they attack 16 rounds, and they say that they can capture these bits, these 40 bits. But when you perform this experiment, you will realize that actually you cannot capture all of the 40 bits because some keys will get the same counters with the correct one. So you wouldn't be able to distinguish which one is the correct one. Okay. So this actually comes from what I observed as differential factors. So let me explain it here. So in the Wang's attack, they had 14 round characteristic and they added 2 rounds. Here, by the way, the probability is 2 to the minus 64 for the single distinguisher, but they observed 24 different characteristics starting with this input difference and having this output difference. So the real probability is actually larger than this. So they claim that they captured 32 bits of the key with this many 2-round encryptions or decryptions. And then they say that remaining 48 bits require 2 to the 48 16-round encryptions, which can perform memory accesses like this. And they say that this attack works because activates at most 6 S boxes in round 16 with input difference 1. Okay, like this. But again, without knowing these 2 S boxes or the round keys, you cannot go from here to here. So this has to be 40 and this has to be 40. But still, you won't be able to capture the whole 40-bit. This is the main difference because we say that in theory, theory and practice are the same, but in practice, theory and practice are never the same, right? So most of the time, attacks cannot be verified in practice due to high data time or memory complexities. Reduced versions of theoretical attacks should be experimentally verified to check if anything is overlooked. And just by chance, I did many experiments in my papers and I observed many errors. Again, just by chance. Wang's attack should be modified due to the existence of differential factors. So this leads us to the notion of differential factors. So this is something I introduced a few years ago when I observed that some theory doesn't match the practice. So here I defined it for S boxes like this. So let's say that SBN S box, M by M S box. So for all XY that satisfy SX XOR SY equals to mu, so we are fixing the input difference. If you also have, when you XOR the inputs with some lambda, non-zero lambda, but if it still gives you the output mu, we say that S box has a differential factor lambda for the output difference mu. In other words, mu remains invariant for lambda. So you might ask why this is important, right? This is important because before the S box operation, we XOR these values with the round keys, right? So I'm saying that now, since I don't know the secret key just before this X XOR value, right? But If XORing it with lambda doesn't affect the output, this means that a secret key K and the secret key of K XOR lambda will always give you the same output difference. This would mean that when you increase the counters, correct key, but also correct key XOR with lambda will have the same counter whatever you do. Increase the number of pairs, perform the experiments with different pairs, it doesn't matter. The counters will be the same because here XOR with lambda does not affect the output difference. And in order to check the correctness of the attack, to check the differential, we are just trying to see if this output is observed. Okay. So this is why actually in practice you cannot capture these keys. Okay, because presence S-box have some differential factors, and just by chance it corresponds to some output difference mu, where that mu is used in these attacks. Okay, so if you use another characteristic, maybe the theory will match the practice because there will not be differential factors there. So for this reason, I strongly suggest everybody to verify every attack in practice.